Hey everyone, we're going to start looking at question 10 from the Chapter 5 practice test, which is a fence problem, or one of the two different varieties of fence problems we're going to be seeing today. So let's get started here on the other screen. So we're building a pen to house goats on a ranch, and you are using the side of your barn and three sides of wood fence. You would also like to have an area of 1,000 square feet for your goats. So the question on part A is what is the minimum amount of fencing you can use? And B, what are the dimensions of that pen? So we're going to use that same uh, steps, I think 6 steps, in order to solve this. So first of all, let's understand our problem. Here we have a diagram of a rectangular pen with well, it has a cow, but I guess it's supposed to be a goat. Anyways, only three sides because the fourth side of this pen is the barn. This side here is going to be congruent to this side here, so we'll call them both X. And this side that's running parallel to the barn, we'll call that Y. And we can really quickly get ourselves a function that tells us how much fence we're going to use. That's going to be a function of x and y, and it's going to be the two x segments plus the y segment. We're on to step 2 now, by the way. Let's get our mathematical model. Well, this is a nice function, but we really need to take that down to one variable if we want to use our methods of calculus that we know for this. So is there something else that we know about this? Well, we know the area is supposed to be 1,000 square feet. So the area of this pen, since it's rectangular, is xy equals 1,000, or just y equals 1,000 over x. Substitute that into the previous equation that we had, and now we have a function of only x. F of x equals 2x plus 1,000 on x. So there's our mathematical model. Step 3 would be to take our derivative and find our critical values. So f prime of x is going to be equal to, well, the derivative with respect to x of 2x plus 1,000 on x. Notice that we do have matching variables, so we can just take the derivative like normal. It's going to be 2 minus 1,000 over x squared. Before we find our critical values, a good thing to do here is to turn this into a rational expression. That's 2x squared minus 1,000 over x squared. Set that equal to 0. Let's consider the domain for x here. Now, clearly, x could be very small. It can actually approach 0. I don't know if it can actually be 0, but for this one, let's pretend that it cannot be 0, and we'll get to that reason why in a minute. But what's the biggest that x could be? Well, if you consider that the dimension y could be approaching 0 as well, you could have a pretty standard, okay looking pen that looks like 50 by 200. That would give you an area of 1,000. But you can also get kind of a whacked out rectangular pen if you wanted to, with an area of 1 to 500. No, 1 to 1,000. Or if you were incredibly crazy, really, you'd be crazy to do this. You could get yourself a pen with a width of zero point 0.1 feet and a length of 10,000 feet. So really, our x dimension, it seems like it can go as long as we need it to do. So this would tell us that we have an infinite domain here. X can go from 0 to 1,000. Of course, I don't know how many goats are going to fit in a fenced-in area that is only 0.1 feet in width. Maybe you might, if you made some kind of an argument that way, you might be able to get a domain for x that is not infinite. But for the sake of this one, we'll just go with the infinite argument. Well, since this is an infinite domain, we can't really use the candidate test. And this is good practice for us because it kind of shows us what to do if we can't use a candidate test. And what we're going to have to do is show that we get an absolute minimum from our critical value. So what are the critical values? Well, critical values occur when the derivative is either equal to 0 or undefined. Part of the reason why we like a rational expression for the derivative is because we can just set the numerator equal to 0 and the denominator equal to 0. And solving those two equations will give us all the critical values. It's just kind of awkward if you want to say, well, when is this function equal to undefined? That's a harder question to answer, really. Definitely not as easy as saying, well, when is this function equal to 0? We're used to solving things when they're equal to 0. We're not used to solving things when they're equal to or when they're undefined. First one is pretty easy. This first equation, that is, we get x squared is equal to, 500. And so that gives us x equal to negative 5 root 10 and positive 5 root 10. Of course, negative 5 root 10 is not in the domain. So we have one critical number from the numerator. The denominator, when is x squared equal to 0? Well, that occurs when x is equal to 0, which, of course, is not in the domain either. So we have one critical number, which means it's looking good for us. Chances are this critical value is either going to be an absolute minimum or an absolute maximum. We just don't know which yet. To find out which, we're going to look at an analysis of the derivative with our good old friend, the number line. So above the number line, we'll put our x's, or values of x, and below that, we'll evaluate our derivative. Our domain begins at 0, and it's an open circle at 0. Let's pretend right over here is 5 root 10. I got this backwards. This is 10 root 5. My mistake. All right, so here's our 10 root 5. And of course, infinity lies off way in that direction. Let's pick a value somewhere between 0 and 10 root 5. And I don't know what 10 root 5 is actually equal to, but I'm going to say that it's definitely less than, or 1 is definitely less than 10 root 5. So we'll substitute 1 into our derivative. We'll figure out f prime of 1. That's equal to, let's see, 2 times 1 is 2 minus 1,000 over 1 squared. Don't bother to do the arithmetic if you don't need to. You know that that's a negative number. So we'll put a negative here, and that means that our f of x is a downward slope. All right, looking good, feeling good. Let's get some number greater than 10 root 5. And I wouldn't recommend you pick something close. Pick something like 100. Yeah, let's pick 100. 100 is definitely bigger than 10 root 5. So what's f prime of 100? That's equal to 2 times 100 squared minus 1,000 over 100 squared. Now, take a look at the magnitude of those numbers. That's why it's nice to pick a number like 100. When you take a look at the magnitude of the numbers, there's no way that 1,000 is greater than 2 times 10,000. It's literally an order of magnitude bigger. So this has got to be a positive result, which means the derivative is positive and the function is increasing. This gives us a pretty good idea that we have a relative minimum at x equals 10 root 5. But is it the absolute minimum? That's a question we want to ask. So if we take apart that entire domain and show that f of 10 root 5 is smaller than every point in that domain, then we've shown that 10 root 5, or f of 10 root 5, is an absolute minimum. Well, if the function decreases between 0 and 10 root 5, that means that f of 10 root 5 has got to be smaller than f of x for all x between 0 and 10 root 5. It has to be, because from 0 to 10 root 5, our function is decreasing. Also, from 10 root 5 to positive infinity, the function is increasing. So 10 root 5 has to be the absolute minimum on that interval too. So 10 root 5, we can just tack it on here. Union with 10 root 5 to infinity. Therefore, f of 10 root 5 is the absolute minimum. Does that answer the question yet? What is the minimum amount of fencing? No, it doesn't. We need to know what f of 10 root 5 is. So let's evaluate f of 10 root 5. We can use any version of f that we want. So I'm going to use, I don't know. I guess we can only use this one right here. So the f of 10 root 5 is equal to 2 multiplied by 10 root 5 plus 1,000 over 10 root 5. Grab your calculator and you will find out that this is equal to 89.44271. That's going to be our absolute minimum. So we'll write our summary statement to reflect that. Our minimum amount of fencing is 89.44271 feet. That's part A. Part B is what are the dimensions of the pen. So to get our dimensions, we're going to take a look. Well, we already know that the x dimension is 10 root 5. The y dimension is, well, it's going to be 1,000 over x, so 1,000 over 10 root 5, which is approximately equal to 44.2721. But come to think of it, it's really kind of unnecessary to write to figure that out, because we can just leave that as 1,000 over 10 root 5. So here's our summary statement for letter B. The dimensions of the pen with the least amount of fencing is 10 root 5 by 1,000 over 10 root 5 feet. So then, that kind of takes care of our problem, and we'll see you next time when we look at more calculus. Bye-bye.